you assume the nearest planet is the quickest to reach. It isn't. Mercury, the closest planet in the solar system, takes longer to reach than worlds 5 times farther from the Sun. Here's what mission planners rarely say out loud. Distance was never the number that mattered. In 2018, the European Space Agency launched a spacecraft toward Mercury that needed 9 separate flybys of 3 different planets just to slow down enough to arrive. 7 years to reach Mercury, 13 months to fly past Jupiter. 5 times farther away, 9 years to reach Pluto, the most distant world any spacecraft has ever touched. Tonight, we'll cross the entire solar system by the only ruler that matters. Not distance, but velocity. We'll watch a spacecraft reach Jupiter faster than another one reaches Mercury. We'll watch the asteroid belt crossed by an engine gentler than a hairdryer, and we'll end at the one destination closer than anything else in the sky, and harder to truly reach than any planet in this atlas. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Every atlas of the solar system starts with the same assumption, and the assumption is wrong before the first stop. It says that distance decides difficulty, that a planet close to Earth must be quick to reach, and a planet far away must be slow. The way a walk across a room is quicker than a walk across a city. The numbers just named are not a coincidence or a curiosity, and they are not the strangest this atlas will produce. They are the entire subject of this episode. Not a ranked list of planets from near to far, but a map of what decides how long a spacecraft takes to arrive somewhere. And it turns out distance is rarely the variable in charge. The label on a planet is its distance from the Sun, the number printed in every textbook diagram and every classroom poster, and it is the number almost everyone uses to guess how hard a mission will be. But the number mission planners work from is different, and it has little to do with miles or kilometers in a straight line. It is the amount of velocity a spacecraft must gain or lose to do what it came to do. Pass by, settle into orbit, or land. And that number depends on gravity, not geography. A planet deep inside the Sun's gravity well, like Mercury, forces anything nearby to move very fast just to avoid falling into the Sun. And a spacecraft that wants to stay near Mercury has to match that speed and then kill most of it, using nothing but momentum, timing, and the gravity of other worlds. A planet far outside that well can be visited by falling toward it and swinging past, borrowing speed rather than shedding it. Distance is the label, velocity is the invoice. And it is the invoice, not the label, that decides the weight. That is the axis this atlas will follow. Not how far a world sits from the Sun, but what a mission has to do with velocity once it gets there, and whether the goal is a glance or a stay. Ordered by that axis, the solar system rearranges itself. Mercury, the closest planet, becomes one of the hardest destinations to settle at. Pluto, 5.5 billion kilometers out, becomes reachable by flyby faster than most people expect. The order a textbook teaches and the order a mission planner lives by are not the same order, and the gap between them is where this atlas begins. With the planet whose reputation for difficulty was earned long before anyone launched a rocket toward it, the assumption this atlas opened by rejecting did not appear from nowhere. And it is worth understanding where it came from before dismantling it further, because a myth built on real information is harder to shake than one built on nothing at all. Since the 17th century, when Johannes Kepler worked out that planets sweep equal areas in equal times as they orbit the Sun, astronomers have known that a planet's distance from the Sun and its orbital period are mathematically linked. Farther planets really do take longer to complete one loop around the Sun, a relationship Kepler's third law states precisely and one that has never been overturned. That is a true, well-established fact about how planets move around the Sun. It is not a fact about how long a spacecraft, launched from Earth, needs to reach one of them, And the two ideas have been blurring together in popular imagination for as long as diagrams of the solar system have hung on classroom walls, showing planets lined up by distance with an implicit suggestion that distance is the only number that matters. Textbook diagrams reinforce the confusion further, almost by design, because they are built to teach scale and order, not mission planning. A poster showing the Sun and 8 planets arranged left to right by distance is genuinely useful for understanding the solar system's structure. And it is genuinely misleading as an intuition for spaceflight because it carries no information about gravity wells, launch windows, or what a mission intends to do once it arrives. Someone reading that poster for the first time has no way to know that the 4th planet from the left will take a lander less time to reach than the first, or that the 5th offers a free ride to nearly everything beyond it. The diagram is not wrong. It is answering a different question than the one this atlas has been asking since its opening lines, and mistaking one question for the other is the single most common error in how people imagine reaching another world. That mistake gets corrected one stop at a time in what follows. Not by discarding the textbook diagram, but by adding the second map it never included. One built from velocity, gravity wells, and mission intent rather than distance alone. Starting with the planet whose difficulty made that second map necessary in the first place. None of this makes Kepler's law less true, and this atlas has no interest in undoing 17th century mathematics that has stood for 4 centuries of testing. Mercury takes about 88 Earth days to complete one orbit around the Sun. Neptune takes about 165 Earth years. That relationship is exact, predictable, and has nothing to do with rockets. What it never claimed to describe was how long a human-built spacecraft, starting from Earth's own orbit, would need to arrive somewhere and either look or stay. Confusing an orbital period with a travel time is an easy mistake to make, and it is the mistake this atlas exists to correct. One carefully documented mission at a time. Picture the poster again for a moment. The one taped to the wall of a classroom or printed in the back pages of a childhood book. You can probably reconstruct roughly where each planet sits on it right now, from memory, because it is one of the most reproduced diagrams in science education. What you cannot reconstruct from it, no matter how carefully you study it, is which of those worlds took a spacecraft 5 months to reach, and which took nearly 7 years. That information was never on the page. It lived somewhere else entirely, in propulsion budgets, launch calendars, and the shape of gravity itself. And this atlas spends the rest of its length filling in what the poster left out. Mercury earned its reputation for difficulty decades before BepiColombo ever left the ground. In November 1973, NASA launched Mariner 10, the first spacecraft aimed at the innermost planet, and it reached Mercury the following March. About 5 months after launch, helped along by a single flyby of Venus that bent its path and trimmed its speed. Compared with what came later, that arrival looks almost casual, but Mariner 10 could only fly past. It photographed Mercury 3 times over the following year, on 3 separate loops around the Sun that happened to bring it back to the same neighborhood, and each time it swept by at several kilometers per second, and kept going, gone again, within hours. It never slowed down enough to stay in orbit, because staying was never part of the plan. A flyby borrows a planet's gravity for a few hours and lets go. An orbiter has to ask for permission indefinitely, and, in orbital mechanics, permission is paid for in propellant, not goodwill. 30 years later, a mission called Messenger tried to stay. Launched in August 2004, it did not fly straight at Mercury the way Mariner 10 had. It looped past Earth once, past Venus twice, and past Mercury itself 3 times before it had finally shed enough velocity to be captured into orbit in March 2011. Nearly 7 years after launch, for a planet, a beam of light crosses from Earth in a matter of minutes. 7 years to reach a near neighbor is the detail that should stop a listener cold. And it is worth sitting with, rather than rushing past. Every one of those flybys existed for one purpose: to steal a small amount of speed from a planet's gravity and hand it to the spacecraft in the opposite direction it was needed, shaving the velocity down in increments too large to manage any other way. There was no shortcut, no more powerful rocket that could have muscled through the problem, because the problem was never really about power. It was about how fast Mercury and everything near it already moves. That speed comes from where Mercury sits. The deeper an object sits inside the sun's gravity, the faster it has to travel just to avoid spiraling in, the same way a ball on a tighter string has to swing faster to avoid falling toward the center. Mercury circles the sun at roughly 47 kilometers a second, noticeably faster than Earth's own orbital speed of about 30 kilometers a second, and a spacecraft launched from Earth carries Earth's speed with it as a kind of inherited habit. To settle into orbit near Mercury, that habit has to be unlearned almost entirely, and unlearning it costs more energy than nearly any other maneuver in the solar system. Gravity assists included. This is the fact that inverts the ordinary intuition about distance. Getting close to the sun does not mean coasting downhill. It means climbing down into a well that gets steeper the farther in you go, and every meter of that descent has to be paid for twice. Once to fall, and once to stop falling. Mercury is not hard to reach because it is far. It is hard to stay near because it is close. BepiColombo, the joint European Space Agency and Japanese mission now making that same 7-year crawl, is a study in how far a strategy has to go to work. It launched in October 2018, carrying 2 separate orbiters bolted together. One built to study Mercury's surface, and one built to study its magnetic field, riding inside a single transfer module whose job is nothing but deceleration. The itinerary reads almost like an apology for how fast Mercury's neighborhood moves. 1 flyby of Earth in April 2020, 2 flybys of Venus in October 2020, and August 2021, and then 6 separate flybys of Mercury itself, spaced across more than 3 years before the spacecraft is finally slow enough, relative to the planet, to be caught into orbit. 9 planetary flybys in total, each one a scheduled appointment with a gravity field. Each one shaving away a little more of the velocity the spacecraft is not allowed to keep. Between flybys, BepiColombo's ion engines run for months at a time, thrusting so gently a person standing on the spacecraft would not feel it, adding their own slow contribution to a deceleration budget too large for chemical rockets to cover in one push. It is worth naming what that budget is for. Because orbit insertion can sound like paperwork rather than physics. To orbit a planet, a spacecraft's velocity relative to that planet has to fall into a narrow window, fast enough that gravity does not pull it straight down, slow enough that gravity can bend its path into a closed loop instead of letting it fly on past. Near Mercury, arriving at the wrong speed does not produce a slightly worse orbit. It produces no orbit at all, just another flyby, which is exactly what happened to Mariner 10 by design, and to no one by accident since. Every gravity assist BepiColombo performs narrows the gap between arrival speed and orbital speed by a small amount, using a planet's own motion as leverage instead of propellant, the same trick a pool player uses when a bank shot is cheaper than a straight one. 9 banked shots, 3 years of drifting between them, and the mission still will not be finished cheaply. It will be finished at all, which near Mercury is the harder achievement. This is the shape of the rule this atlas opens with. Distance told mission planners almost nothing useful. What told them everything was how fast the neighborhood already moves, and how much of that speed had to be surrendered before the spacecraft could belong there, instead of just passing through. Mercury is close. Getting there quickly was never the problem. Staying was. Picture the fuel gauge on a conventional rocket for a moment. It does not go up. Every gravity assist BepiColombo performs is, in effect, a free refill drawn from a planet that will never miss the loan. Chemical propellant, by contrast, is fixed the moment the rocket leaves the pad. There is no refueling station between Earth and Mercury, no depot waiting in the dark, A mission that tried to cancel Mercury's velocity using propellant alone would need a spacecraft too heavy for any rocket currently built to lift off Earth at all. That constraint, more than any single design choice, is why 9 flybys in 7 years were never a failure of engineering. They were the engineering. BepiColombo's own mission planners have described the itinerary less as a schedule and more as a series of negotiations. Each flyby timed to the day, sometimes to the hour, because missing one appointment with a planet's gravity does not delay the mission. It can force an entirely different, longer sequence to be flown instead. That precision is part of why patience in this atlas keeps turning out to be a form of engineering rather than a form of waiting. 2 missions, 1 planet, and 2 completely different timelines make the pattern impossible to miss once it is named. Mariner 10 reached Mercury in about 5 months because it only needed to pass by. Messenger needed nearly 7 years to reach the same planet because it needed to stay. And BepiColombo needs roughly the same 7 years for the same reason, repeated with a longer list of flybys behind it. The label on Mercury, its distance from Earth, never lied, and it never once matched the invoice a mission had to pay. The planet did not move. The distance did not change between one mission and the next. What changed was the question each spacecraft was built to answer, and that question decided almost everything about how long the trip would take. That gives this atlas its first working rule. Provisional, the way every rule in this map will be provisional until the next stop tests it. How long it takes to reach a planet depends less on how far away that planet sits, and more on how much velocity a spacecraft must gain or shed to do what it was sent to do, and a planet deep inside the Sun's gravity well demands an especially large amount of shedding before anything is allowed to stay near it. By that rule, Mercury should be one of the hardest planets in the solar system to settle at, despite being one of the easiest to glimpse. And that is exactly what nearly 60 years of missions have shown. It also predicts something about every other planet in this atlas before a single one of them has been visited in this telling. Wherever a mission's job is only to look, the trip should be relatively quick. Wherever a mission's job is to stay, the trip should stretch, sometimes by years, regardless of how the destination sits on a printed diagram of the solar system. A rule that only explains the planet it was built from is not much of a rule. The next stop, the planet immediately outside Mercury's orbit, agrees with part of it and quietly breaks another part. And that disagreement is where the map starts to earn its shape. It helps to say the rule once more, plainly, before moving on, because the rest of this atlas leans on it repeatedly. Ask a spacecraft only to look, and the Sun's gravity well barely matters. A flyby borrows speed and keeps it. Ask a spacecraft to stay, and the well matters more than almost anything else in the mission's design, because staying means giving that borrowed speed back. Mercury asked the second question first, before anywhere else in the solar system had a chance to answer it. Every stop after this one will ask a version of the same 2 questions, in a different gravity well, with a different planet's own motion available to borrow from. Some of the answers will look nothing like Mercury's. That is not the rule breaking. It is the rule doing exactly what a working rule is supposed to do, describing a pattern precisely enough that a genuine exception becomes visible when one finally shows up. Venus is where that exception waits, close enough that this atlas barely has to travel to find it. Venus, one planet closer to Earth than Mars, and one planet farther from the Sun than Mercury, breaks the rule in a direction nobody expects on first hearing it. It should sit somewhere in the middle of this atlas's difficulty scale, deep enough in the Sun's gravity well to demand real deceleration, but not nearly as deep as Mercury. In practice, reaching Venus has been almost easy from the earliest days of spaceflight. Mariner 2, launched in August 1962, reached it in December of the same year. About 3.5 months, the fastest successful planetary encounter of its era, and the first time any spacecraft from Earth reported data from beside another world. No exotic gravity assist made that possible. Venus and Earth sit close enough, and Venus's own gravity well is shallow enough that a direct, almost brute force trajectory works for a flyby. Dozens of missions since have used Venus the same way, not as a destination, but as a waypoint, a planet close enough and convenient enough to visit almost in passing on the way to somewhere else. That ease is exactly what makes Venus useful to every other stop on this atlas. A gravity assist works by borrowing a small amount of a planet's own orbital momentum and handing it to a passing spacecraft. And Venus, sitting close to Earth's orbit and moving at a brisk pace of its own, is one of the most convenient lending institutions in the solar system. Mariner 10 borrowed from it to reach Mercury in 1974. Messenger borrowed from it twice on the way to the same planet 3 decades later. BepiColombo is borrowing from it twice more right now. Parker Solar Probe, a mission this atlas will reach later, borrows from Venus 7 separate times over its working life, using the planet almost as a repeating tool rather than a one-time favor. Venus, in other words, is easy to visit and useful precisely because it is easy to visit. And that combination makes it one of the busiest intersections in the solar system, rather than a quiet planet waiting its turn. Consider what convenient cost across 6 decades of Venus missions. Mariner 2's success in December 1962 came after Mariner 1, its predecessor, was destroyed less than 5 minutes after launch that same year, lost to a single mistyped guidance instruction. Venus, in other words, was never free even at its easiest. It demanded a different kind of cost than Mercury does. Fuel and trajectory were cheap. Precision, on the very first attempts, was not. That distinction matters here, because it is easy to hear 3.5 months and imagine an unremarkable errand, when in fact Mariner 2's flight was the first time humanity had ever successfully sent anything to another planet and lived to analyze the data. It was not always convenient. It became convenient, the same way Mars's later reputation for quick, reliable landings was earned by a program that lost several spacecraft before Viking ever worked. None of that ease, though, means Venus is a forgiving place, and the next stop on this atlas is the exception that keeps this rule from becoming too tidy. Getting somewhere quickly and surviving once you arrive are two completely different questions, and Venus answers them in opposite directions. Reaching Venus's neighborhood is easy. Surviving there is a different kind of problem. One this atlas's velocity rule was never built to explain, and naming that limit honestly matters more than pretending one rule covers everything. The Soviet Venera program spent nearly 2 decades, from the 1960s into the early 1980s, learning that Lesson 1 destroyed spacecraft at a time. Early landers were crushed, cooked, or both before they could transmit a single useful reading, because Venus's atmosphere carries roughly 90 times the pressure of Earth's at the surface, wrapped around a world where daytime temperatures sit hot enough to melt lead. Venera 7, in December 1970, became the first spacecraft to transmit data from the surface of another planet, and it survived barely 23 minutes before the heat and pressure finished it. Later landers in the series improved on that, but none lasted more than about 2 hours, and none was ever expected to last much longer. This is where distance and velocity stop being the whole story, and where an honest atlas has to widen its own rule rather than force Venus to fit it. Venus is easy to reach because it sits close and moves conveniently for a gravity assist. It is nearly impossible to survive on because its atmosphere, not its orbit, is the obstacle, and no amount of clever trajectory planning changes what waits at the bottom of that pressure and heat. A mission's difficulty, it turns out, is not one number, but at least 2. How hard it is to arrive, and how hard it is to endure once you have. Mercury scores high on the first and moderate on the second. Venus scores low on the first and brutally high on the second. Keeping both numbers in view, rather than collapsing them into a single idea of difficulty, is what keeps this atlas honest as it moves outward. And it is what the next stop, the planet most people assume is the easy one, will test from the opposite direction. Because 90 times Earth's atmospheric pressure and hot enough to melt lead can slide past a listener as abstractions rather than physical facts. 90 times Earth's surface pressure is roughly what a submarine hull withstands nearly a kilometer beneath the ocean. Except at Venus, that pressure exists in open air, under an orange sky, with no ocean required to produce it. The heat is not a desert heat that fades at night. Venus's thick atmosphere traps it evenly across the entire planet, dayside and nightside alike, so there is no cooler hemisphere to retreat toward and no evening relief. A lander does not fail at Venus the way a battery fails. Slowly, with warning, it fails the way a sealed container fails when the pressure and temperature outside exceed what any material was built to hold, all at once, usually within minutes of touchdown. That is a genuinely different kind of difficulty than anything Mercury poses. And this atlas has no single number to compare them by. Mercury's difficulty is measured in years, and gravity assists, a problem of motion. Venus's difficulty, once landed, is measured in minutes and structural failure, a problem of endurance. Both are real. Neither cancels the other out, and both are a long way from what most people imagine when they picture a planet close enough to visit easily, which is exactly the imagination this atlas keeps testing. One destroyed spacecraft and one successful orbiter at a time. 4 stops into this atlas, the title's promise starts to come into focus, and it is worth stating plainly before moving further out. How long it takes to reach a planet depends on which question a mission is asking. If the question is how fast can something fly past, distance and a well-chosen gravity assist answer it, and the answer is often measured in months, sometimes for planets that sit shockingly far away. If the question is, how long until something can stay, land, or survive, the answer depends on gravity, wells, atmospheres, and engineering limits that have very little to do with how far a ruler would measure between 2 points in space. Mercury is close and brutal to settle near. Venus is close and easy to reach, then brutal to survive. Distance alone predicted neither result. That reframing opens a bigger debt than any single planet has paid off so far, because it raises an obvious next question. What happens to this rule at the planet most people already assume is simple? Mars sits farther from the Sun than Earth. Outside Earth's own gravity well, rather than deep inside anyone else's, and popular culture has spent decades treating a trip there as the next logical step after the Moon. Difficult, certainly, but understandable, almost routine compared with a place like Mercury. That assumption is not entirely wrong, and it is worth testing carefully rather than confirming or breaking it for the sake of a clean narrative. Mars is where this atlas's rule gets its cleanest confirmation yet, and also where a popular myth about easy space travel was quietly built, mission by mission, on real data that people later stopped reading carefully. Distance predicted nothing at Mercury. It predicted nothing at Venus. Mars is where it finally gets a fair trial. The myth deserves examination because it explains where the distance equals difficulty assumption came from in the first place. Mars missions, more than any other set of planetary missions, are the ones most people have half memorized. A launch, a several-month cruise, a landing broadcast live, a rover trundling across red dust within the same news cycle. That familiarity created an intuition that space travel generally works this way. Fast for a nearby planet, slower for a distant one. And the intuition held up because nobody was comparing it against Mercury or Jupiter at the same time. Mars is not proof that distance predicts travel time. It is proof of what happens when a planet's orbit and a spacecraft's goal happen to line up conveniently, and the next 2 stops show exactly how narrow that convenience is. 2 questions, 2 answers. One number never applied to both. That is the whole shape of what this atlas has argued so far, condensed into 3 short lines. And Mars is the fairest test of it yet, because nothing about Mars has been rigged in this rule's favour the way Mercury and Venus might seem, on first hearing, almost too extreme to trust. Consider the alternative for a moment. If distance alone predicted difficulty, Venus should have been moderately hard, and Mars should have been the hardest planet visited yet. Farther out, with no assist chain behind it, and no obvious shortcut. Neither happened. The pattern broke exactly where the old assumptions said it should hold, and it held exactly where the old assumptions said it should break. Mars missions really have been fast, and the record backs up the popular intuition further than most people realize. Viking 1, launched in August 1975, entered orbit around Mars in June 1976, about 10 months after leaving Earth, and its lander touched down the following month to begin the first fully successful surface mission on another planet. Nearly 45 years later, Perseverance made the same kind of trip even faster. Launched in July 2020, it did not stop in orbit at all, driving straight through the atmosphere to a landing in February 2021, about 6.5 months after launch. 2 different decades, 2 different mission designs, and both landed on Mars in under a year. Compared with Mercury's 7-year itinerary of borrowed velocity, Mars looks almost obliging. Part of that ease is genuine, and part of it is timing. Genuinely, Mars sits outside Earth's own orbit rather than deep inside the Sun's gravity well, the way Mercury does. So a spacecraft headed to Mars is moving in roughly the same direction the Sun's gravity already wants it to go, coasting outward rather than fighting to slow down against an increasingly steep gravitational slope. That is real physics. And it matters. But timing matters just as much, and it is the part popular accounts usually skip. Earth and Mars line up for an efficient transfer only once every roughly 26 months, when the 2 planets' positions allow a spacecraft to launch along a curved path that meets Mars where it will be rather than where it is at launch. Miss that window, and the same trip can cost far more fuel, or far more time, or both. Perseverance, Viking, and nearly every successful Mars mission since the 1970s launched inside one of those windows on purpose, which means the 6 to 10 month figure people remember is not how long Mars takes. It is how long Mars takes when a mission is patient enough to wait for the planets to cooperate first. It is worth naming exactly what happens to a mission that cannot wait. Earlier Mars missions that launched during less favorable alignments within the same 26-month cycle, or that missed a window entirely, have taken considerably longer and required significantly more propellant to arrive at all. Some stretching well past 9 months for a trip that a well-timed launch completes in 6. NASA and other agencies plan Mars launches years in advance, specifically to avoid ever needing to test that penalty in a real mission, which means the 6 to 10 month figure people remember is not an average. It is closer to a best case, deliberately engineered to be the only case anyone flies. That distinction between the easiest possible version of a trip and the trip itself recurs throughout this atlas, and Mars is where it first becomes impossible to ignore. A textbook diagram cannot show a launch window. It cannot show the 26-month clock ticking in the background of every successful Mars mission since the 1970s. It only shows distance, frozen in a single moment, and distance alone would never predict that Mars. Outside Earth's orbit, farther from the Sun, and part of no gravity assist chain at all, could be reached faster than Venus without ever pushing for extra speed. The clock, not the ruler, produced that number. The physics underneath that convenience is worth spelling out, because it is the cleanest confirmation this atlas has found yet for its working rule. In 1925, the German engineer Walter Hohmann described the most fuel-efficient way to move a spacecraft from one roughly circular orbit to another, a single elliptical path tangent to the starting orbit at one end and the destination orbit at the other, requiring exactly 2 engine burns and no more. For a trip to an outer planet like Mars, that ellipse stretches outward from Earth's orbit, using the Sun's own gravity to decelerate the spacecraft gently as it climbs, the opposite of Mercury's problem entirely. A Mars-bound spacecraft does not need to shed enormous velocity to be captured. Because Mars's own gravity well is shallower than Earth's, let alone the Sun's inner reaches, and Mars orbits the Sun more slowly than Earth does rather than faster. Everything about the geometry cooperates. This is the confirmation the rule needed and the qualifier it also needed. Confirmation. A planet outside a deep gravity well, approached along an efficient transfer orbit, really can be reached in well under a year, exactly as the rule predicts for a mission that is not fighting steep deceleration. Qualifier. Well under a year only holds when the mission also respects the calendar, launching inside the roughly 26-month window when Earth and Mars align for that efficient Hohmann path. A mission that ignores the window does not become impossible, but it becomes dramatically more expensive in fuel or time, sometimes both, which is its own quiet proof that velocity, not raw distance, is doing the real work here. Mars is not easy because it is close. It is comparatively easy because its gravity well is shallow and its calendar is forgiving. And the next stop tests what happens once a mission has to leave that calendar's comfort zone behind entirely. It helps to make the Hohmann geometry concrete rather than leaving it as an abstract ellipse. Imagine stepping off a moving walkway in an airport at exactly the right moment to land on a second, slower walkway heading in roughly the same direction, timed so your speed and the second walkway's speed already nearly match when you step across. That is what an efficient Mars transfer does with orbital velocity. Earth's own speed around the Sun, about 30 kilometers a second, already carries most of what a Mars-bound spacecraft needs. The engine burn at departure adds only the difference. A comparatively small nudge rather than a dramatic push. And Mars's own gravity, weaker than Earth's, absorbs the spacecraft gently rather than requiring a hard cancellation of speed. Compare that walkway to the one at Mercury. There, stepping across would mean leaping onto a walkway moving dramatically faster in the opposite direction. One that offers no gentle overlap in speed at all. No single step solves that mismatch. It has to be closed gradually. Contact by contact, planet by planet. Which is exactly what BepiColombo's 9 gravity assists are doing on a walkway. Mercury refuses to make easy. Mars's forgiving geometry is not a law of nature that favors red planets over grey ones. It is what happens when a spacecraft's inherited speed and a destination's required speed already point in nearly the same direction before the engines ever ignite. Past Mars, the rule this atlas has been building meets a variable it has not needed yet. Not gravity wells or calendar windows, but the kind of engine doing the work. The Dawn mission, launched in September 2007, was aimed at 2 targets in the asteroid belt that no earlier mission had visited in orbit: Vesta and Ceres, the 2 largest bodies between Mars and Jupiter, and reaching either one the conventional way, with chemical rockets, would have demanded more propellant than any single launch could reasonably carry. Dawn solved that problem by not being in a hurry. It flew on ion propulsion, a system that ionizes xenon gas and accelerates it through an electric field rather than burning chemical fuel, producing thrust so gentle it has been compared to the pressure of a sheet of paper resting on an open palm. That thrust ran almost continuously for years rather than in short, powerful bursts, and the patience paid for capability no chemical rocket could match. Dawn entered orbit around Vesta in July 2011, left it in 2012, and entered orbit around Ceres in March 2015, becoming the first spacecraft in history to orbit 2 separate bodies beyond Earth on a single mission. None of that would have been possible on the rule this atlas has used so far, which has mostly asked how much velocity a mission needs to gain or lose. Dawn's real constraint was never really velocity in the abstract. It was how quickly that velocity could be supplied. Chemical engines deliver enormous thrust in minutes and then go silent for the rest of the trip. Ion engines deliver a whisper of thrust that never really stops, trading raw power for efficiency measured over months and years instead of seconds. The total velocity change Dawn achieved over its mission was larger than almost any other spacecraft in history has managed. A genuinely record-setting figure, and it did not come from a single dramatic burn. It came from patience distributed across nearly 8 years between launch and its final orbit. Propulsion sets how quickly a mission can afford to pay whatever that target costs, and the two variables do not always move together. It is worth putting a number on what patience distributed across years means, because ion engines are easy to underestimate on first description. Dawn's ion thrusters produced a maximum thrust roughly comparable to the weight of a single sheet of paper resting in an open hand. A tiny fraction of a newton, depending on power available at the time. A chemical rocket engine, by comparison, can produce a thrust measured in hundreds of thousands of newtons for a few minutes at a time. On paper, ion propulsion looks almost too weak to matter. In practice, thrust that never stops eventually outperforms thrust that only fires in bursts, the same way a small, steady stream of water will eventually fill a tank faster than a series of short, powerful bursts separated by long pauses. Once enough time is allowed to pass, that patience is precisely what let Dawn attempt something no chemical mission before it had even proposed seriously. Visiting 2 separate worlds in orbit, on one spacecraft, on one budget. It did not need a gravity assist to solve its velocity problem. It needed years, and an engine willing to spend them. Slow, it turns out, was the whole strategy. What Dawn proved by orbiting 2 worlds instead of one is easy to undersell if the achievement is treated as a curiosity rather than a genuine expansion of what reaching a planet can mean. Every mission before it that entered orbit around another body had done so once, spending essentially its entire propulsion budget on that single capture and having nothing left to leave again in any controlled way. Dawn left Vesta on purpose, using its ion engines to climb back out of that world's gravity well over months of gentle thrust, then crossed the gap to Ceres and repeated the capture process a second time, arriving in March 2015 with enough control remaining to settle into a stable, long-term orbit rather than falling past. The mission's own name, chosen before launch, referred to studying the dawn of the solar system through 2 of its oldest surviving building blocks, and the double orbit achievement made that comparison possible in a way a single flyby of either body never could have. Set beside Mercury's 7-year itinerary, Ceres presents an odd twist. A target roughly as demanding in total velocity change, reached by an entirely different kind of patience. BepiColombo pays its debt through borrowed momentum, planet by planet, timed against 3 separate worlds' gravity. Dawn paid a comparably large debt through sustained, gentle acceleration that never depended on any other planet cooperating at all, only on years of uninterrupted thrust and a mission team willing to let a spacecraft take its time. Both strategies solve the same underlying problem: how to change velocity by a large amount without carrying an impossible mass of chemical fuel. And both confirm, from opposite directions, that the number worth tracking across this atlas is never how far a target sits from Earth. It is how much velocity a mission has to buy and what currency it pays in. There is a quieter detail in Dawn's story worth pulling forward, because it says something about how this atlas has been measuring difficulty all along. Vesta and Ceres are not identical worlds, and reaching each one required a different amount of velocity change, calculated separately by Dawn's mission planners years before launch. Vesta, smaller and drier, needed one budget. Ceres, larger and icier, needed another. A single ion engine, thrusting patiently across the gap between them, absorbed both budgets without ever refueling, without ever docking, without any human intervention beyond commands sent across tens of millions of kilometers. No chemical mission in history has managed that combination, and none is currently planned to try, because the propellant math still does not favor it. What Dawn demonstrates in the end is that the velocity a mission has to buy, this atlas keeps returning to, is never a single fixed number attached to a planet. It is a number attached to a specific spacecraft, a specific engine, and a specific plan, and the same destination can cost wildly different amounts of time depending on which of those three variables a mission is willing to trade against the others. Ceres, reached by patience rather than power, is the clearest proof yet that the map this atlas is building was never really a map of planets at all. It is a map of trade-offs, redrawn every time a new mission chooses which currency it can afford to spend. 5 stops in, the rule this atlas opened with needs an honest update, because Mercury's velocity story and Dawn's propulsion story are both true, and neither one alone explains everything seen so far. The revised version reads like this: how long it takes to reach a planet depends on how much velocity a mission must gain or shed to accomplish its actual goal, how steep the gravity well is at the destination, and what kind of propulsion is available to pay that velocity bill. In one enormous burn, in a sequence of borrowed gravity assists, or in years of continuous, gentle thrust, none of those three factors is optional, and no single one of them, taken alone, would have predicted Mercury's 7 years, Mars's 7 months, or Ceres' nearly 8 years for a target that, on a printed diagram, looks far closer to Mars than to Mercury in difficulty. That revision also predicts something specific about what comes next, and specific predictions are what make a rule worth keeping rather than merely descriptive. Jupiter sits 5 times farther from the Sun than Earth, deep enough outside the inner solar system that a direct trajectory should, in principle, take a very long time. Yet Jupiter is also massive enough that its gravity offers one of the most powerful assists available anywhere in the solar system, capable of flinging a spacecraft toward the outer planets at speeds nothing launched from Earth alone could match. If the revised rule holds, a flyby of Jupiter should be faster than intuition expects, precisely because Jupiter's own gravity does so much of the work once a spacecraft gets close enough to use it. An orbiter, on the other hand, has to cancel a meaningful share of that same gravity's pull to stay, which should stretch its timeline the same way Mercury's timeline stretched, just for a different reason and at a very different scale. It is worth stating what would falsify this revised rule, because a rule that cannot be proven wrong is not doing useful work. If a mission reached Jupiter by flyby in, say, 5 years despite having every reason to move faster, no unusual trajectory, no mission requirement demanding a slower path, that would suggest something other than velocity and gravity wells was governing the timeline, and this atlas would owe its listener an honest correction rather than a forced fit. If an orbiter mission somehow settled into orbit around a giant planet in under 2 years, using no unusual technology, that would suggest the staying costs years. Half of the rule was too strong. Neither of those things has happened yet, in nearly 50 years of outer planet missions, and that consistency is itself a form of evidence. This atlas is not asking for blind trust in a pattern, it is asking a listener to watch the pattern survive contact with increasingly difficult cases. A planet, then 2 very different planets, then an asteroid belt, then a gas giant, approach 2 different ways. Jupiter is the largest test yet, both in raw scale and in how cleanly 2 real missions aimed at the same world for different reasons are about to confirm exactly what the rule predicts. The rule is short. Look, borrow speed, stay, repay it. Everything else in this atlas is that sentence, tested 7 more times against 7 more worlds, including one that is not a planet at all. Pioneer 10 tested that prediction before almost any theory of gravity assists had been proven in practice. Launched in March 1972, it became the first spacecraft to cross the asteroid belt and the first to reach Jupiter, arriving in December 1973, about 21 months after launch. for a planet sitting roughly 5 times farther from the Sun than Earth. At the time, Pioneer 10 also left Earth faster than anything humans had ever launched, escaping Earth's gravity on a direct, high-energy trajectory, rather than looping through any intermediate gravity assists, because none had yet been engineered into a mission of this kind. Even without borrowed momentum from another planet, distance alone did not translate into the years intuition might expect. 21 months to a world 5 times farther than Earth is a fraction of what Mercury's much shorter distance ended up costing 2 different orbiter missions decades later. Jupiter's own gravity, once Pioneer 10 arrived, did the rest of the era's real work for the missions that followed. Voyager 1, launched in September 1977, reached Jupiter in March 1979, about 18 months after launch, and used the encounter not merely to take photographs, but to bend its own trajectory and gain enough additional speed to reach Saturn in November 1980, roughly 3 years and 2 months after leaving Earth, using Jupiter's gravity the way a slingshot uses tension. Borrowed, brief, and enormously effective. None of that speed came from Voyager's own engines. It came from Jupiter's mass, more than 300 times Earth's, redirecting and accelerating a spacecraft that could never have carried enough fuel to reach that velocity on its own. A flyby of a giant planet, it turns out, is not merely fast, despite the distance involved. It is fast partly because of the distance involved, since only a very massive, very distant world offers a gravitational assist powerful enough to make the rest of the outer solar system reachable at all. Pioneer 10's achievement is easy to undersell because it happened first. Before gravity assists were a familiar concept, and before missions routinely borrowed velocity from planet to planet as a matter of course, its own instruments were modest by later standards. Built to survive an asteroid belt that engineers in 1972 were not entirely sure any spacecraft could cross safely, given how little was known at the time about the density of debris scattered between Mars and Jupiter. Pioneer 10 proved the belt was passable, then kept going, then proved a giant planet's gravity could be studied up close without destroying the spacecraft that approached it. Every mission that followed, Voyager, Galileo, Juno, New Horizons, inherited that proof and built on it rather than repeating the experiment from scratch. There is something worth pausing on in that inheritance. None of the fast, efficient flybys later in this atlas would have been attempted with the same confidence if Pioneer 10 had not gone first and reported back that the physics worked as predicted. Speed, in other words, was never only a matter of trajectory design, it was also a matter of accumulated trust. Built mission by mission, in a set of equations that looked good on paper long before anyone had watched them play out hundreds of millions of kilometers from home. The gravity assists that have carried nearly every spacecraft in this atlas past or into orbit around a planet deserve a plain explanation, because the phrase gets used often without ever quite being unpacked, and understanding it changes how the rest of this atlas reads. A gravity assist works by conservation of momentum, the same physical law that lets a moving billiard ball transfer speed to a stationary one on contact. Except nothing here touches anything else. As a spacecraft approaches a planet on the correct trajectory, the planet's gravity bends its path and changes its speed relative to the planet, but by the time the spacecraft leaves the planet's gravitational influence, its speed relative to the planet has returned to almost exactly what it was on approach. What has changed is the spacecraft's speed relative to the Sun, because the planet itself is moving, and the encounter effectively lets the spacecraft borrow a small slice of the planet's own orbital momentum. The planet does lose a tiny, genuinely immeasurable amount of its own speed in the exchange, a debt too small to ever detect against a body carrying the mass of a moon or a world, while the spacecraft gains, or, arranged the opposite way, loses, a slice large enough to reshape an entire mission. The direction of that exchange depends entirely on the geometry of the approach. Fly behind a planet relative to its direction of travel, and the spacecraft picks up speed. The trick Voyager 1 used at Jupiter and the outer planet missions used repeatedly after it. Fly in front of it, and the spacecraft loses speed instead. The trick BepiColombo and Messenger have used repeatedly at Venus and Mercury, and the trick Parker Solar Probe uses at Venus on its long fall toward the Sun. Neither maneuver requires a single drop of propellant beyond the fine corrections needed to hit the geometry precisely, which is why gravity assists have become the default tool for nearly every long-distance or high-precision mission since the 1970s. They convert a planet's own existing motion into a resource available for free to any mission willing to plan its trajectory carefully enough and wait long enough for the right alignment. That waiting is the part rarely mentioned outside mission planning documents. And it belongs in this atlas because it explains why so many of the timelines already covered stretch across years rather than months. A single gravity assist can only be used when the spacecraft and the planet occupy the right positions relative to each other. A window that might open once a year, once every few years, or, in Voyager 2's case at the outer planets, once every century and 3/4, every extra flyby a mission needs, at Venus or Mercury or anywhere else, adds not just the maneuver itself, but the waiting between opportunities. And that waiting, multiplied across 9 flybys at Mercury or 7 at the Sun, is where most of BepiColombo's and Parker Solar Probe's 7 years goes. Picture it happening to something you can hold. Roll a marble past a spinning fan blade at just the right angle, and the blade's motion nudges the marble's path and speed by a small, real amount without the blade ever touching it or slowing down in any way you could measure by hand. A planet does the same thing to a spacecraft, at a scale of hundreds of millions of kilometers rather than centimeters, and at a scale of kilometers per second rather than a light nudge across a tabletop. The physics is identical. Only the numbers change. New Horizons made the case even more starkly 3 decades later. And the contrast is sharp enough that it belongs at the center of this atlas rather than in a footnote. Launched in January 2006 at the fastest speed any spacecraft had ever left Earth, it reached Jupiter in February 2007, about 13 months after launch, and used the planet's gravity to gain speed on its way toward Pluto, rather than to slow down for any kind of capture. 13 months to a planet 5 times farther from the Sun than Mercury sits is about as close as this atlas comes to a clean confirmation of its rule. In its simplest form, ask only for a glance, and even an enormous distance collapses into a short trip. Then compare that to Galileo, a mission that wanted to stay. Launched in October 1989, Galileo did not fly a direct path to Jupiter at all, because the powerful upper stage rocket originally planned for its launch was cancelled after the 1986 Challenger disaster. Galileo had to fly a far less energetic route, looping past Venus once and Earth twice, in a sequence engineers nicknamed VE-GAY, the Venus Earth-Earth Gravity Assist, gathering speed in stages, the way BepiColombo gathers deceleration in stages near Mercury. That indirect path meant Galileo did not reach Jupiter until December 1995. Just over 6 years after launch, nearly 5 times longer than New Horizons would take to reach the very same planet a decade later. The distance never changed between the 2 missions. What changed was the goal. New Horizons only needed to pass through Jupiter's gravity once, briefly, and keep moving. Galileo needed to survive its own trajectory limitations and still arrive slow enough, eventually, to be captured into orbit rather than flung past like everything that came before it. It is worth imagining the 2 control rooms side by side, decades apart, to feel the difference these numbers describe, rather than only hear it. In 2006, New Horizons team watched a spacecraft cross Jupiter's orbit and keep accelerating outward, checking off a single flyby's worth of instructions before turning its attention almost entirely toward a target still 9 years away. In 1995, Galileo's team spent 6 years managing a spacecraft that had survived an antenna failure, a damaged main communications dish that never fully deployed, and a trajectory built around 3 separate planetary flybys before Jupiter ever came into clear view. A mission defined as much by patient troubleshooting as by trajectory design. Both teams eventually succeeded. Neither team's success looked anything like the others. And the gap between 13 months and 6 years is really a gap between 2 entirely different kinds of mission management, not merely 2 different flight paths. That gap also explains something about risk that distance alone cannot capture. A short flyby mission like New Horizons concentrates almost all of its risk into a single day, the one day of closest approach, and spends the rest of its crews essentially coasting and waiting. A long orbiter mission like Galileo spreads risk across years in which a hardware failure, a software fault, or a missed course correction can quietly end a mission long before it ever reaches its destination. 6 years is not a longer number than 13 months. It is 13 months worth of risk, repeated across roughly 5.5 more years of exposure to everything that can go wrong in deep space. Juno completes the comparison and removes any remaining doubt about which variable governs the timeline. Launched in August 2011, it reached Jupiter and entered orbit in July 2016, just under 5 years after launch, using a single Earth flyby along the way rather than Galileo's more elaborate 3-planet detour, and benefiting from a more powerful rocket than Galileo had been forced to use. Even with a more direct route and a stronger launch, Juno still needed nearly 5 years to do what New Horizons had done for a flyby of the same planet in 13 months. The difference between those 2 missions has nothing to do with which rocket was better or which trajectory was cleverer. It has everything to do with what happened after arrival. New Horizons kept its velocity and kept moving, while Juno had to shed a substantial share of its speed relative to Jupiter to be captured into a stable orbit, a maneuver that took a long, carefully managed engine burn once the spacecraft arrived, and years of trajectory planning before that to set up the burn correctly. Jupiter, in other words, replays Mercury's lesson at an entirely different scale and proves it is not a quirk specific to the innermost planet. A world's own mass and gravity make it a spectacular source of free velocity for anything willing to fly past and keep going. And the exact same mass and gravity makes settling into orbit around it expensive in time, if not always in fuel, for anything that wants to stay. Distance told none of this story. Mission goal told all of it. Saturn, one planet farther out and reachable only by an even longer coast for anything not using Jupiter's assist, is where this same pattern gets tested a third time at a distance great enough that even the flyby numbers start to look, for the first time in this atlas, genuinely large. Juno's orbit insertion burn itself deserves a moment of attention, because it is the kind of event that decided the entire mission in roughly half an hour. On the night of July 4, 2016, Juno's main engine fired for about 35 minutes, cancelling enough of the spacecraft's speed relative to Jupiter to let the planet's gravity catch it into a long, looping orbit instead of flinging it back out into deep space. Mission controllers on Earth could do nothing but wait during that burn, because a radio signal from Jupiter takes roughly 48 minutes to reach Earth, meaning the outcome was already decided, one way or another, before anyone on the ground even knew the engine had ignited. 5 years of trajectory planning, gravity assist timing, and fuel budgeting all resolved into a single half hour that nobody could intervene in. Watch, live, or redo. That is the sharp edge hiding inside every years to orbit figure in this atlas. The years are not spent slowly, gradually arriving. They are spent traveling toward one short, unforgiving window, and everything before that window exists only to make sure the spacecraft reaches it with exactly the right speed, in exactly the right place, at exactly the right time. Voyager 1's trip to Saturn already appeared briefly in this atlas as part of Jupiter's story, and it deserves a fuller look on its own terms because it is one of the clearest demonstrations available of how much a single gravity assist can compress a supposedly long-distance trip. Saturn orbits nearly twice as far from the Sun as Jupiter does, and almost 10 times farther than Earth, distant enough that a direct trajectory from Earth would ordinarily be measured in many years. Voyager 1, launched in September 1977, reached Saturn in November 1980. About 3 years and 2 months after launch, almost entirely because its earlier flyby of Jupiter, 18 months into the mission, redirected its path and added a substantial amount of velocity no onboard engine could have supplied. Saturn's own gravity did the rest during final approach, curving Voyager 1's path close enough to study the planet's rings and largest moons in detail before flinging it onward out of the solar system entirely, on a trajectory it still follows today. 3 years and 2 months to reach a world nearly 10 times farther from the Sun than Earth is a genuinely strange number to sit with, stranger than Mercury's 7 years to reach a world that never leaves Earth's general neighborhood by comparison. It only makes sense once Jupiter's role in the trip is counted as part of the destination rather than a mere waypoint passed along the way. Every gravity assist chains one planet's velocity onto a spacecraft's path toward the next, and Saturn, positioned conveniently beyond a planet as massive as Jupiter, becomes far more reachable by flyby than its raw distance from the Sun would ever suggest on its own. The next question, the one that gives this stop its full shape, is what happens when a mission at Saturn wants what Juno wanted at Jupiter. Not a look, but a stay. It is worth noticing what Voyager 1 gave up in exchange for that speed, because every gravity assist carries a hidden trade. Once a spacecraft uses a planet's gravity to gain velocity for the next leg of a journey, its own trajectory is set by that encounter. There is no changing course afterward to slow down and look longer. No return trip to study something that caught the mission team's attention only after the data came back. Voyager 1 spent barely a day within close range of Saturn, gathering as much data as its instruments and the era's communication bandwidth allowed, then continued outward on a path that would eventually carry it beyond the solar system entirely. Speed purchased with a gravity assist is rarely free of that condition. It buys a shorter trip and, almost always, a shorter visit once the spacecraft finally arrives. That trade is not a flaw in the strategy. It is the price printed in fine text beneath every gravity-assisted flyby this atlas has covered. From Pioneer at Jupiter to Voyager 2 at Neptune, still years away in this telling. Cassini answered that question the same way Messenger and Juno had answered it at their own planets, by trading years for velocity control. Launched in October 1997, Cassini did not fly the direct, high-speed trajectory Voyager 1 had used. It looped past Venus twice, then Earth, then Jupiter, on a sequence of gravity assists that gathered speed gradually rather than all at once, arriving at Jupiter in December 2000 before finally reaching Saturn and entering orbit in July 2004. Nearly 7 years after launch, more than twice as long as Voyager 1's flyby, for a mission that wanted to stay for over a decade rather than pass through in a matter of days. That patience produced one of the most productive planetary missions in the history of spaceflight. 13 years in Saturn's system, the discovery of active geysers erupting from the moon Enceladus, detailed studies of Titan's methane lakes, and a final, deliberate plunge into Saturn's atmosphere in September 2017, timed to protect any moons that might harbour life from contamination by the spacecraft itself. Set beside Voyager 1's 3-year flyby, Cassini's 7-year arrival tells the same story Mercury told at the opposite end of the solar system. Just written at outer planet scale, a gravity assist chain can deliver a spacecraft to almost any planet, near or far, in a time that has far more to do with which other planets happen to be available for borrowing velocity than with the raw distance being crossed. But every assist that adds velocity for a flyby has to be answered, eventually, by an equal and opposite subtraction if the goal is to stay, and that subtraction is rarely free. Two atlases exist inside the same solar system, in other words. One built for spacecraft that only intend to look, and one built for spacecraft that intend to remain, and they do not share a timeline, even when they share a destination. Cassini's 13 years in Saturn's system are worth measuring against what a flyby could never have delivered, because the discovery of Enceladus's geysers illustrates the difference precisely. Voyager 1 and Voyager 2 both photographed Enceladus in passing in 1980 and 1981 and saw a small, unusually bright moon with almost no craters. An interesting but ambiguous observation, gone again within hours, with no way to investigate further. Cassini, by contrast, was still in the system 25 years later, when its instruments detected plumes of water ice erupting from Enceladus's south pole, and rather than moving on, it changed its own orbit repeatedly over the following decade, to fly directly through those plumes, sampling their chemistry multiple times, building a case for a subsurface ocean that a single pass could never have supported with real evidence. That is what 7 years of arrival time buys, beyond the raw fact of getting there. A mission able to notice something unexpected and then change its plan to chase it. A flyby has no such flexibility. It sees what it happens to see. On the one day it happens to be looking, and then it is gone. The years Cassini spent shedding velocity to arrive were also, in a sense, years it spent buying the freedom to be surprised and to respond to that surprise. It is worth pausing here, roughly 2/3 of the way through this atlas by planet count, though nowhere close to finish by argument, to draw the two maps this pattern has been building side by side. The flyby map, so far, reads Venus in about 3.5 months, Mars in 6 to 10 months depending on the calendar, Jupiter in 21 months without any assist at all, or 13 months with one borrowed from Jupiter's own gravity on the way to somewhere farther, and Saturn in about 3 years using Jupiter as a springboard. Distance still matters on this map, but it bends dramatically wherever a bigger planet's gravity is available, partway along the route. The orbiter map reads almost nothing like it. Mercury in about 7 years, Jupiter in 5 to 6 years depending on the trajectory forced by launch conditions, Saturn in nearly 7 years, each number stretched far past what the flyby map would predict for the same world. Neither map is more correct than the other, and treating one as the real answer to how long a trip takes is where most casual explanations of space travel go wrong. They are answers to two different questions wearing the same planet's name, and this atlas has tried, at every stop so far, to keep both questions visible, rather than quietly picking one and calling it the whole truth. The next two stops complicate both maps at once, because they involve two planets no spacecraft has ever attempted to orbit at all. Not because the mission would be uninteresting, but because nobody has yet been willing to pay what an orbiter at that distance would cost. Uranus and Neptune sit at the edge of both maps this atlas has drawn, visited exactly once each, by the same spacecraft, on a single pass that will not be repeated for a very long time. It is worth being precise about what complicate means here, because this atlas has no interest in manufacturing drama where none exists. Uranus and Neptune do not break the rule built across the previous 6 stops. They have not tested the half of it that concerns staying, because no mission has ever asked that half of the question at either planet. A rule untested in one region of its domain is not a rule disproven. It is a rule with an honest gap, and honest gaps are different from contradictions. This atlas has already met one genuine exception, at Venus, where ease of arrival and ease of survival pulled in opposite directions. Uranus and Neptune are not that. They are the two stops where humanity has only ever asked the cheaper question, and never yet paid for the more expensive one. That distinction matters enough to spend the next 2 stops on, because conflating an untested rule with a broken one is exactly the kind of shortcut this atlas has tried to avoid since its opening minutes. 2 maps, 1 solar system. Neither map lies, and neither map alone would have been enough to answer the question this atlas opened with. That is worth repeating before the ice giants take center stage, because the temptation to flatten 2 honest maps into 1 convenient number is exactly the temptation that produced the original assumption this atlas has spent its length correcting. Voyager 2 is the only spacecraft in history to have visited Uranus. And it did so only once. On a single flyby in January 1986, about 8.5 years after its August 1977 launch. By the time it reached Uranus, Voyager 2 had already used gravity assists from Jupiter in July 1979 and Saturn in August 1981 to bend its trajectory outward again, a chain of borrowed momentum stretching across 3 planets and nearly a decade, each assist setting up the geometry for the next. Uranus itself is a strange stop on any map. It orbits on its side, tilted so far that its poles point almost directly at the Sun during parts of its 84-year orbit, and Voyager 2's flyby captured nearly all of the direct scientific knowledge humanity currently holds about it. No orbiter has ever been sent. No lander has ever been attempted. Everything known about Uranus's rings, its confirmed moons at the time of the flyby, and its unusually weak, lopsided magnetic field traces back to a matter of hours in January 1986, a single close pass that will not be repeated by any operating spacecraft for the foreseeable future. That single visit is itself a data point worth taking seriously rather than skipping past as a curiosity. Nothing about Uranus's distance from the Sun, roughly 19 times Earth's, makes it categorically unreachable. Voyager 2 reached it in well under a decade, using the same assist chaining strategy that got Voyager 1 to Saturn in 3 years. What has kept any mission from staying is not physics but priority and cost. An orbiter capable of shedding enough velocity to be captured near Uranus would need either a very long, patient trajectory or an amount of propellant far beyond what any mission budget to date has been willing to commit to a single ice giant. The rule this atlas has followed all along still applies. It has never been tested here, because nobody has yet chosen to spend what the test would cost. It helps to imagine what Voyager 2's brief window at Uranus looked like from the ground. The spacecraft signal, by January 1986, took about 2¾ hours to reach Earth, meaning every image, every measurement, arrived long after the moment it was taken, filtering in across a delay wide enough that a listener at Mission Control could have made coffee, returned, and still been waiting for confirmation that a single command had been received. Because the flyby was so brief and sunlight at Uranus so faint compared with Earth's, engineers pushed the spacecraft's cameras and data systems to their design limits just to capture usable images at all, slowing the spacecraft's data transmission rate and using longer exposure times than any earlier Voyager encounter had required. Every photograph of Uranus's pale, nearly featureless blue-green disk that exists today, in every textbook and documentary since, traces back to that one narrow window of exposure settings and light-starved cameras, calibrated for a single pass that could not be repeated if anything had gone wrong. Nothing did. But the margin for error, by the mission's own account, was thin enough that this atlas can call the resulting images a record of engineering as much as a record of the planet itself. Voyager 2 kept going, and its arrival at Neptune in August 1989, about 12 years after launch, remains the farthest flyby of a planet any spacecraft has ever completed. A record that has stood for more than 3 decades and shows no sign of being broken soon. Neptune orbits roughly 30 times farther from the Sun than Earth, distant enough that sunlight itself takes about 4 hours to make the trip one way, and Voyager 2 reached it using yet another gravity assist from Uranus 3.5 years earlier, extending a chain of borrowed velocity that by this point had passed through 4 separate planets since leaving Earth. The flyby lasted only a matter of hours, close enough to reveal Neptune's great dark spot, a storm system roughly the size of Earth, and to discover several of its moons for the first time, including close images of Triton, a moon whose icy geysers and backward orbit suggest it was captured from elsewhere rather than born alongside its planet. 12 years to reach the farthest planet in the solar system, using nothing but chained gravity assists and a single, well-timed launch window in the late 1970s that let one spacecraft visit 4 giant planets in sequence, is the flyby map's most extreme entry and its clearest proof of concept at the same time. That launch window, sometimes called the Grand Tour alignment, occurs roughly once every 175 years, when Jupiter, Saturn, Uranus, and Neptune line up in a configuration that allows a single spacecraft to assist chain its way through all 4, rather than choosing just 1 or 2. Voyager 2 is, so far, the only mission to have used it for that full sequence, and no similarly efficient path to Neptune will present itself again for well over a century. Reaching the farthest planet quickly, it turns out, was never only a matter of distance, or even of clever assists. It also required a specific arrangement of the outer solar system that happened to exist exactly when humanity was ready to launch. Consider the round-trip communication delay involved in flying past Neptune in the first place, because it shapes how differently that encounter had to be planned compared with anything closer to Earth. A radio signal from Neptune takes about 4 hours to reach Earth one way, meaning a command sent in response to something Voyager 2 observed would not produce a result at the spacecraft for roughly 8 hours round trip. Far too slow for any kind of real-time control during the few hours the flyby itself lasted. Every instruction Voyager 2 executed at Neptune had been written, tested, and uploaded months in advance, timed to the second, because there was no possibility of adjusting on the fly once the encounter began. That is a detail easy to lose inside a simple number like 12 years, and it deserves naming plainly. The entire Neptune flyby, the discovery of the Great Dark Spot, the first close images of Triton's icy plumes, happened inside a spacecraft essentially running on its own judgment, guided by instructions written by people who would not know whether any of it had worked until light itself had crossed the gap and come home. No spacecraft has ever orbited Uranus or Neptune, and it is worth being precise about why that gap belongs in this atlas as an honest unknown rather than as a hidden failure or a secret. It is not that orbiting either planet is physically impossible. The same principles that let Messenger settle at Mercury and Juno settle at Jupiter would apply in modified form at either ice giant. It is that no mission has yet been funded, designed, and launched to attempt it. A matter of engineering projection rather than measured history. The Planetary Science Decadal Survey, a report produced roughly once every 10 years by the U.S. National Academies to recommend priorities for NASA's next generation of missions, named a Uranus orbiter and atmospheric probe its top priority for a large flagship mission in its 2023 report, the clearest signal yet that the agency and the wider planetary science community consider this gap worth closing. If such a mission launches in the early 2032, as some proposed timelines suggest, current trajectory studies estimate a cruise of roughly 12 to 15 years to Uranus, using a combination of gravity assists. A figure this atlas labels a model-based projection rather than a measured fact, because no spacecraft has flown that exact route, and the number will shift as mission design matures. That honesty matters more here than at almost any other stop, because it is tempting to round an estimate into a certainty because the topic is exciting to talk about. This atlas will not do that. What can be said with confidence is this: the ice giants are the clearest remaining test of the rule built across every previous stop, and they remain untested, not because the physics forbids an answer, but because no one has yet paid to find it. Distance, once again, is not the obstacle. Willingness to spend years and money on velocity is, and for Uranus and Neptune specifically, that willingness has not yet turned into a launch. It is worth naming what an eventual Uranus orbiter would need to accomplish, because the challenge is not fly there and stop. Uranus's extreme axial tilt means its magnetic field and radiation environment behave unlike any other planets, complicating both the trajectory an orbiter would fly and the instruments it would need to survive the encounter. Proposed mission concepts, studied in preparation for the 2023 Decadal Survey, considered several different approaches, including using a radioisotope power source rather than solar panels, since sunlight at Uranus carries only a small fraction of the intensity it does at Earth. Far too weak to reliably power a spacecraft the way sunlight powers missions closer to the Sun. None of those concepts has yet been approved for construction, funded for launch, or assigned a firm departure date. That is the honest state of this stop in the Atlas. A destination understood well enough, in principle, to plan a mission toward it in detail, and not yet prioritized highly enough against every other competing use of a space agency's budget. To build one, the physics is not the barrier. The cue is. It helps, before this Atlas turns toward its final 2 stops, to let the numbers gathered so far settle rather than rushing straight into the next comparison. 7 years to stay near Mercury, 3.5 months to glimpse Venus, 6 to 10 months to land on Mars, if the calendar cooperates, 13 months to pass Jupiter, 5 years to orbit it, 3 years to pass Saturn, 7 to stay, 8.5 years to the only look humanity has ever taken at Uranus, 12 years to the only look at Neptune, and no number at all yet for what staying at either would cost, because no one has tried. None of those figures came from the same kind of trip, and holding them all in mind at once is less like memorizing a schedule and more like learning to read a new kind of map, one where the scale changes depending on what a traveler intends to do once they arrive. There is something almost restful in that realization. Once it settles, the solar system is not an obstacle course ranked by difficulty from near to far, punishing distance and rewarding proximity in a straightforward line. It is closer to a negotiation, held individually with every world, between how fast that world already moves, how steep its gravity runs, and how patient or impatient the mission designers on Earth were willing to be. Mercury's difficulty and Venus's ease exist side by side without contradicting each other, because they were never answering the same question. That is not a loophole in the rule this Atlas has followed. It is the rule working exactly as advertised, at a scale small enough to hold in a single breath before the next 2 stops push it as far as it will go. First toward a target so far away that even a flyby sounds implausible, and then toward the one object in the solar system that is, in the most literal sense, closer than anything else discussed so far, and somehow still among the hardest to reach. There is a specific kind of quiet worth allowing here. The kind this channel exists to offer, not the absence of information, but the settling of it. Nothing about the numbers just listed needs to be memorized. What is worth carrying forward into the final 2 stops is simpler than any individual figure. The sense that a spacecraft's clock and a planet's position on a diagram were never reading the same watch. One measures a straight line through space. The other measures a negotiation with gravity, propulsion, and patience, conducted separately with every world it touches. Both are real. Only one of them predicts how long a listener would have to wait for news of an arrival. Let that settle for a moment before the Atlas turns toward its final and strangest case. The one destination close enough to see with unprotected eyes at dusk, and distant enough, in every way this Atlas has learned to measure distance, that no spacecraft has ever truly arrived. Say the numbers once more, short version: months for a glance, years for a stay, nothing yet for 2 worlds still waiting their turn. Pluto sits roughly 5.5 billion kilometers from the Sun, at its average distance, more than 39 times farther out than Earth, and for most of the 20th century, it stood as the single most distant object anyone seriously proposed sending a spacecraft toward. New horizons, launched in January 2006, left Earth faster than any spacecraft in history, crossing the orbit of the Moon in just 9 hours and reaching Jupiter, as this atlas noted earlier, in about 13 months. It kept that speed and, using Jupiter's gravity to add still more, continued outward for nearly 8.5 additional years before reaching Pluto in July 2015, about 9.5 years after launch in total, closing a gap that many scientists in earlier decades had assumed would take considerably longer to cross with any available technology. 9.5 years to reach the most distant major body this atlas has covered sounds, on first hearing, like it should confirm the simplest version of distance equals time that this entire episode has been quietly dismantling stop by stop. It does not. Once the comparison is made honestly, 9.5 years to a target 39 times farther than Earth is, proportionally, a far shorter trip than BepiColombo's 7 years to a target that never leaves Earth's general neighborhood in the sky. New Horizons reached Pluto as quickly as it did precisely because it never intended to stop, carrying no capability for orbital insertion at all, and because it launched at the highest velocity ever achieved by a spacecraft leaving Earth, a decision made specifically because Pluto's extreme distance demanded speed be treated as the mission's central design problem from day one. Distance did shape this mission, more directly than almost any other stop in this atlas, but it shaped the engineering choices that made the trip fast. Rather than dictating how long the trip would take, it is worth remembering what New Horizons carried into that speed record, because the spacecraft itself was built light and lean specifically to make such velocity achievable at all. It weighed roughly half a ton at launch, small compared with orbiter missions like Cassini or Galileo, because every extra kilogram would have required additional propellant just to reach the same departure speed, and additional propellant would have meant additional mass. In a compounding problem familiar to every rocket engineer since the earliest days of spaceflight, New Horizons carried no orbit insertion engine, no large fuel reserve for slowing down, and no backup plan beyond the single trajectory it had been given at launch. Every choice the mission's designers made, from the size of its antenna to the power of its plutonium generator, served the same underlying goal: leave Earth as fast as physically possible and never look back. That single-mindedness is what makes New Horizons the cleanest possible test case for the flyby half of this atlas's rule. It is not a mission that happened to be fast. It is a mission built, component by component, around the assumption that speed alone, chosen deliberately and paid for at launch, rather than borrowed gradually along the way, could compress a 9.5-year trip across the widest gap this atlas has covered. The 9.5-year figure carries a weight that deserves to be named plainly, because it is unlike almost every other number in this atlas. Every mission discussed so far that entered orbit could recover from a missed encounter, adjust its trajectory over months or years, and try again if an instrument needed recalibrating along the way. New Horizons had exactly one chance at Pluto. Its flyby speed, roughly 14 kilometers per second relative to Pluto, meant the entire scientific encounter, every photograph, every spectral reading, every measurement of Pluto's thin nitrogen atmosphere and its large moon Charon, happened within a window of a few hours on a single day in July 2015, planned years in advance down to the second, with no possibility of a second attempt if anything went wrong. The mission team spent nearly a decade of cruise time preparing instructions for a handful of irreplaceable hours, a ratio of preparation to execution that has no real equivalent among the orbiter missions elsewhere in this atlas. That single, irreversible encounter is the honest cost of choosing speed over capture, and it belongs in the same conversation as Mercury's 7 years and Cassini's 13 years at Saturn, not as a separate category, but as the far end of the same trade-off this entire atlas has been tracing. A mission can move fast by refusing to slow down. And refusing to slow down means refusing, permanently, the chance to look twice. Pluto, at 9.5 years and one uninterruptible pass, is where that trade-off shows its full price most clearly. precisely because the distance involved is large enough that nobody could pretend the choice was easy or the stakes were small. The final stop takes the opposite extreme of nearly every variable this atlas has tracked: distance, velocity, and patience alike. It is worth imagining the room where that single day was managed, because the emotional weight of one chance is easy to state and harder to feel without a concrete picture. On July 14, 2015, the New Horizons team gathered at Mission Control, unable to receive any images during the closest approach itself because the spacecraft's single antenna could not observe Pluto and transmit data to Earth at the same time. For several hours, the team had no way of knowing whether the flyby had succeeded, whether an instrument had failed, whether a stray piece of debris in the Pluto system, a real risk the mission had studied carefully beforehand, had struck the spacecraft during the fastest, closest part of its pass. Confirmation that New Horizons had survived and executed its full observation sequence did not arrive until the following day, transmitted across several hours of light travel time from a spacecraft that had, by then, already moved on, incapable of turning back regardless of what the data eventually showed. That gap between action and confirmation is its own kind of distance, separate from kilometers and separate from years of cruise time, and it belongs in this atlas as one more way the Sun's neighborhood refuses to be measured by a single number. The Sun sits about 150 million kilometers from Earth, closer by far than any planet this atlas has visited, close enough that its light reaches human eyes in about 8 minutes. By the logic this atlas opened by rejecting, reaching it should be the easiest trip of all, closer even than Venus, let alone Mercury. It is, instead, arguably, the hardest destination described in this entire map. And the reason is the same reason Mercury proved difficult at the very beginning. Gravity near the Sun is not a gentle decline that a spacecraft can fall into. It is closer to the mouth of the well this atlas has referenced since its opening minutes, the steepest gravitational slope in the solar system, and anything that wants to get genuinely close has to shed an amount of velocity that dwarfs even what BepiColombo spends reaching Mercury. Say the distance out loud, and it sounds like nothing. 150 million kilometers. Closer than every planet in this atlas. Closer than Venus. Closer than Mercury. And still, for 6 decades of spaceflight, untouched at close range, because closeness on a ruler and closeness in a gravity well are not the same fact, no matter how many times a listener has been told otherwise. The Sun does not sit still and wait to be measured either. It rotates, sheds material in solar wind, and reshapes the space around it with magnetic fields that stretch out past every planet in this atlas, including the 2 nobody has ever managed to orbit. A spacecraft approaching it is not approaching a fixed point the way a spacecraft approaches a solid planet. It is approaching a boundary that moves, flares, and occasionally reaches out to meet the spacecraft halfway, sometimes violently, in bursts of charged particles. No planetary flyby in this atlas has ever had to survive. It helps to name exactly how much steeper that slope becomes as a spacecraft approaches the Sun, rather than merely asserting that it does. Mercury orbits at roughly 47 kilometers a second, already faster than any planet farther out. The material in the Sun's own outer atmosphere, the corona that Parker's solar probe was built to fly through, moves at speeds that make Mercury's orbital pace look unhurried by comparison, because it sits so much deeper inside the same gravitational curve that everything in this atlas has been climbing down since its opening minutes. A spacecraft does not gently coast toward that environment. It has to be caught by it, gradually, the same way Mercury's orbiters had to be caught. Except the well here does not level off at any point close enough for a single mission to solve it in one pass. That is the plain physical reason no spacecraft reached the Sun's immediate neighborhood for 6 decades after the first satellites reached orbit around Earth. It was never a question of engines powerful enough to get there quickly. It was a question of finding a way to arrive slowly enough, patiently enough and precisely enough to survive being caught by gravity that's steep without burning up or flying straight through. Parker Solar Probe, launched in August 2018, was built specifically to answer that challenge, and its strategy makes the loop this atlas opened with feel complete rather than merely echoed. Instead of one dramatic maneuver, it performs a sequence of 7 separate gravity assists from Venus, spaced across roughly 7 years, each one trimming its orbit a little tighter and its closest approach to the Sun a little nearer. The same borrowing and shedding strategy BepiColombo uses at Mercury applied here against a gravity well an order of magnitude steeper. On its closest passes, completed in the final years of its primary mission, Parker Solar Probe came within about 6 million kilometers of the Sun's visible surface, closer than any human-made object in history, moving at roughly 690,000 kilometers an hour relative to the Sun, the fastest any spacecraft has ever traveled. That speed is not the product of a single powerful launch. It is the accumulated result of falling, again and again, a little deeper into the steepest gravity well in this atlas, with Venus lending a hand every single time. Each of those 7 Venus flybys did exactly what Mercury's flybys and Saturn's single Jupiter assist did earlier in this atlas: borrow a small, precise amount of velocity from a planet's own motion and hand it to the spacecraft in whatever direction the mission needed. For Parker Solar Probe, the direction needed was inward, shedding orbital energy relative to the Sun bit by bit, rather than gaining speed to travel outward the way Voyager or New Horizons did. Venus, sitting conveniently between Earth and the Sun, made an ideal repeated partner for that work, agreeing to lend momentum 7 separate times across the mission's planned lifetime without ever needing to be visited in a way that risked damaging the spacecraft, since each flyby stayed a comfortable distance above Venus's crushing atmosphere. By the final flybys, Parker Solar Probe's orbit had tightened enough to carry it through the Sun's outer atmosphere. The corona, a region so hot in temperature yet so thin in density that specially engineered heat shields could protect the spacecraft's instruments even while the corona itself burned at temperatures. The sun-facing side of that shield was built to withstand. 7 years and 7 gravity assists to get close to the nearest star is, when set beside BepiColombo's 7 years and 9 gravity assists to get close to the nearest planet, close enough in shape that it stops looking like a coincidence and starts looking like confirmation. Both missions target objects that sit, in raw distance, closer to Earth than almost anything else discussed in this atlas. Both missions needed the better part of a decade and a chain of borrowed planetary momentum to get there safely. Distance told neither mission planner anything useful about how long the trip would take. What told them everything was the same number this atlas named at its very first stop: how much velocity has to be surrendered, and how patiently a spacecraft can afford to surrender it. It is worth being specific about what the heat shield on the sun-facing side of Parker Solar Probe experiences during a close pass, because the number is easy to state and hard to picture. During its closest approaches, that shield's outward face reaches temperatures hot enough to soften most metals, while instruments mounted on the shaded side of the same spacecraft, a few meters away, operate at close to room temperature, protected by a shield engineered specifically to prevent that heat from conducting through. The spacecraft, in effect, carries its own steep gradient, the same way the Sun's gravity carries a steep gradient in velocity. An extreme condition on one face, ordinary conditions immediately behind it, separated by a boundary engineered to hold. That symmetry is not an accident of description. Every stop in this atlas has, in one way or another, been a story about managing a gradient. Of velocity near Mercury, of pressure and heat near Venus, of light and cold near Uranus and Neptune, and now of heat and shielding near the Sun itself. Distance never predicted any of those gradients cleanly. What predicted them, every time, was a precise physical description of the environment a spacecraft would meet once it arrived, translated carefully into engineering, rather than assumed from a number on a diagram. Say what 7 Venus flybys and 7 years brought, one more time, without the metaphor. Not distance closed, velocity surrendered, in careful, repeated installments, to a star too massive to approach any faster than its own gravity allows. That is the whole transaction, stripped of imagery, years traded for closeness, at a price fixed by physics rather than by ambition. At the start of this atlas, the label on a planet was named as its distance from the Sun, the number in the textbook diagram, and the invoice was named as something else entirely. The velocity a mission has to pay for, in propellant, in patience, or in years spent borrowing gravity from other worlds. The label on Mercury reads about 77 million kilometers from Earth at its closest approach, nearer than almost anything else in this atlas. The invoice reads 7 years and 9 gravity assists. The label on the Sun reads about 150 million kilometers, the smallest number attached to any destination in this entire episode. The invoice reads 7 years and 7 gravity assists. A fleet of spacecraft scorching passes through the hottest environment any human-made object has ever entered, just to get close enough to matter scientifically. It is worth resisting, one final time, the temptation to call this a twist, because nothing about it required trickery to reveal. Every fact assembled here was public record well before this atlas began. BepiColombo's itinerary is published by the European Space Agency. Parker Solar Probe's trajectory is published by NASA and the Johns Hopkins Applied Physics Laboratory, the institution that also built New Horizons. Nobody hid the pattern. It required setting Mercury's mission timeline beside the Sun's mission timeline, something the two agencies involved had little reason to do themselves, since one team was focused on a planet and the other on a star. An atlas exists precisely to make comparisons. No single mission report is designed to make on its own. To hold two timelines that were planned separately, published separately, and executed years apart, and let them answer the same question together. That is the quiet argument underneath everything this episode has covered. Difficulty in the solar system was never hiding. It was scattered across dozens of separate mission plans, filed under separate agencies, described in separate units, until someone asked the same question of all of them at once, and let the pattern show itself. That is the shape this atlas has been drawing since its opening minutes, stop by stop, planet by planet, until the two nearest large objects in Earth's sky turned out to demand nearly identical strategies to reach. It is not a coincidence, and it was never meant to feel like a twist ending revealed at the last possible moment. It is the same rule, tested honestly against every kind of target the solar system offers. Near and far, small and massive, easy to glimpse, and nearly impossible to survive. And it held every time a mission's goal was named specifically enough to test it against. Distance decided almost nothing on its own. What a spacecraft needed to do with its own velocity, once it arrived, decided almost everything. And the Sun, of all places, turned out to be where that lesson closes the loop. It opened with a much smaller, much colder planet at the very beginning of the night. Laid out one more time, in full, this atlas looks nothing like the diagram most classrooms still use. Organized by how long a flyby takes. Venus in about 3.5 months, Mars in 6 to 10 months when the calendar cooperates, Jupiter in 13 months with a gravity assist or 21 without one, Saturn in about 3 years using Jupiter's assist, Uranus in 8.5 years, Neptune in 12, and Pluto in 9.5. A list where distance still roughly predicts order, but only because every one of these missions chose speed over capture and let gravity assists do as much work as physics allowed, organized instead by how long it takes to stay. Mars in 6 to 10 months to land directly, Mercury in nearly 7 years to orbit, Jupiter in 5 to 6 years depending on trajectory, Saturn in nearly 7 years, and the Sun in 7 years to approach as closely as engineering currently allows without ever fully arriving in any traditional sense. A list where the old order collapses completely, and the planet everyone assumes should be simplest, because it is nearest, sits closer to the hardest end of the scale than the easiest. Two atlases, drawn from the same 60 years of missions, tell two different stories about the same solar system, and neither map is wrong. The mistake was ever expecting one map to answer both questions at once. A ruler measures distance faithfully and says nothing reliable about difficulty, because difficulty was never a property of the space between 2 points. It was always a property of what a spacecraft owed in velocity once it got there, and to whom, and how patiently that debt could be paid. A lesson this atlas relearned at every single stop, from a small, scorched planet at the very beginning of the night to the star that planet orbits at the very end of it. It is worth returning, one last time, to the poster this atlas opened by questioning. The one with 8 or 9 circles marching outward from a yellow sun, distance encoded neatly in the space between them. That poster is not wrong, and nothing in this atlas asks a listener to throw it away. It is incomplete, the way a map showing only elevation would be incomplete for someone planning a hike that also depends on trail conditions, weather, and how much daylight remains. Distance from the sun is real, measurable, and useful for exactly one kind of question. Where does this planet sit relative to the others? Right now, in space. It was never built to answer the question this atlas exists to answer, and expecting it to do so was the entire misunderstanding this atlas opened by naming. A better poster, if one were ever drawn, would need 2 axes instead of 1. Distance along the bottom, the way the old one worked, and something like velocity owed on arrival, running up the side, bending Mercury and the Sun sharply upward while leaving Mars and Venus's flyby routes close to the ground. No such poster hangs in any classroom yet, but the missions that generated every number in this atlas have already drawn it, mission by mission, whether or not anyone put it on a wall. So, how long does it really take to reach every planet? The honest answer, the one this atlas has spent its length earning rather than assuming, is that reach is not one question but at least 2, and the answer changes completely depending on which one is being asked. To glimpse every planet in this solar system, a single flyby of each, gathering data and moving on. The fastest missions on record suggest a trip of a few months for the nearest worlds, and roughly a decade for the farthest. DOM's farthest, with a well-timed sequence of gravity assists doing more to shorten that decade than any single rocket ever could. To stay at a planet, to enter orbit or land, and remain there long enough to study a world rather than glance at it, the timeline stretches unevenly across the solar system, from about 6 months at Mars, the one genuine bright spot where patience is rewarded by fortunate geometry, to nearly 7 years at Mercury, Jupiter, and Saturn alike, 3 planets that could not be more different in distance, yet arrive at almost the same number once the true cost is counted honestly. And 2 planets, Uranus and Neptune, do not have an answer at all yet, not because physics forbids one, but because no mission has been funded to find out, a gap this atlas has tried to name honestly rather than paper over with a confident-sounding guess. That gap is itself part of the answer, maybe the most important part. How long was never a fixed property of the solar system, waiting to be measured once and settled. It is a question that changes shape depending on what humanity is willing to build, willing to wait for, and willing to spend. And every number in this atlas, from 3.5 months to 7 years to a decade to nothing measured at all, is a record of a choice someone made, not a law the universe imposed from the outside. Say the whole answer in one breath. One last time. A glance costs months, sometimes a decade for the very farthest world. A stay costs years, sometimes the better part of one, no matter how close the target sits on paper. 2 ice giants cost nothing yet, only because nobody has spent what a stay there would require. 3 sentences. That is the entire episode. compressed, and everything before this moment existed only to earn the right to say it this plainly. It is worth being equally honest about what this atlas cannot promise, because a clean answer delivered with false confidence would undo everything the ledger behind this episode was built to protect. Every number here reflects missions that have flown, using propulsion and trajectory techniques that existed at the time of each launch. Future missions, using more powerful engines, more efficient ion propulsion, or trajectory designs not yet invented, could shorten some of these numbers considerably, the same way New Horizons' launch speed shortened what earlier decades assumed a Pluto mission would require. This atlas describes what has been achieved, carefully and specifically, not a ceiling on what spaceflight will always cost. The two ice giants without an orbiter, more than any other stop in this atlas, are proof that the numbers here are a record of choices already made, not a boundary already reached. That distinction is the last thing worth carrying out of this atlas, and into whatever comes next in the solar system's exploration. Distance was never the obstacle. Propulsion and patience were never fixed, and the map this episode has drawn is a snapshot of a system still very much being explored. One gravity assist, one launch window, and one funded mission at a time. Somewhere above the atmosphere tonight, a handful of the spacecraft named in this atlas are still moving, still paying off debts of velocity they took on years or decades ago. BepiColombo is still threading its last flybys past Mercury, closer with each pass to finally settling into the orbit it left Earth to reach. Parker's solar probe is still tracing its tightened loops past Venus, grazing closer to the Sun's corona than anything built by human hands has survived before it. Voyager 1 and Voyager 2, past every planet this atlas visited, keep drifting outward at the same borrowed speed that carried them past Jupiter and Saturn. And, for Voyager 2 alone, past Uranus and Neptune too, carrying instruments that still faintly report back across a gap. Starlight itself takes hours to cross. None of them are lost, they are still paying, in time, what distance alone was never able to explain. That is the shape of the answer this atlas leaves behind. Not a ranking from near to far, but a map of debts, each one specific to a world and a goal, each one paid in exactly the currency that world demanded. Months for a glance, years for a stay, and in two cases, no payment made yet at all, only a plan waiting for its turn. The planets have not moved from where they have always been. What has changed, slowly and expensively, one gravity assist at a time, is how precisely humanity has learned to ask them for velocity, instead of asking them for distance, and to expect the right kind of answer back. Picture, for a moment, the very first stop this atlas made, back before any of these later numbers had accumulated. A small, grey, sun-scorched world, closer to Earth than almost anything else in the sky, carrying a reputation for difficulty that took decades of missions to fully explain. That planet has not gotten any closer or any farther since this atlas began. What has changed in the time it has taken to walk through 9 planets, 1 dwarf planet, a scattered asteroid belt, and a star is how precisely a listener can now say why Mercury was always going to be hard, and why the Sun, sitting even nearer, was always going to be harder still. Precision like that is its own kind of arrival. Not a spacecraft settling into orbit, but an idea settling into place. The same slow, deliberate way a gravity assist bends a trajectory, a few careful degrees at a time until, eventually, an entire mission has changed course. Nothing about the solar system asked to be understood this way. It sat there, moving the way it has always moved, indifferent to which of its worlds humans found easy and which they found impossible, while decades of engineers quietly built the missions that would eventually answer a question nobody could have answered by looking at a diagram alone. That patience, spread across 60 years and dozens of spacecraft, is the real subject this atlas has been circling since its very first sentence. The universe will still be here when you wake up. So will we. Good night.